Yeah, turn it on.
Yeah, turn on.
So on. It's flashing.
Cool. 1 second. Okay,
Good.
do you want to just give us a clap while you're on camera? Okay, cool. Now I can sync you on here. Alright.
Hello. Hello everybody, and I'd like to thank Professor Dawley and UTS for giving us time to give this talk. Today I'll be talking about a subject that's of great personal interest to me, that I think it's quite an interesting topic that definitely, if you're doing mathematics, you should be exposed to it. This concept which I'm talking about is called the brachistochrone. So brachistochrone comes from the Greek word shortest time. So it's a problem that has a long history. It's been used in a variety of contexts, and we're just going to go through some brief examples of where this concept has been applied, mostly in a mathematical physics sort of context, but basically we're going to turn this problem on its head and use it to do some physical mathematics. So the classical version of this problem goes back to the Bernoulli brothers in 1696, and it says, given any 2 points in a plane, what is the curve traced out by a point acted on by gravity, which starts at A and ends at B, such that the time taken over between A and B is least. So basically we've got a little point here which is acted on by gravity, okay, and it slides down the curve. Okay, what is the curve that takes us from A to B in least time? So we're not going to go into the mechanics of this. This problem is well known since 1696 and was solved as a challenge problem by Sir Isaac Newton, I believe, and he solved it in 1 day. Okay, and so the answer to this is the cycloid. So I mean, a lot of people will be familiar with the cycloid, and that they'll know the classical problem. You have a point on the surface of a wheel, okay, and as the wheel rolls around, it generates the curve which we call the cycloid. Okay, so that's that. Now, the quantum version of this problem says, given any 2 quantum states, what is the Hamiltonian operator? Okay, which we'll define. Okay, which drives the quantum state from state A to state B in least time. So you can see that how these two problems correspond to each other. Now, there's an associated principle which goes along with this called the quantum Fermat principle. The Fermat principle, which is going back to slightly before the brachistochrone, okay, which says that light travels by the path of least time. Okay, and there's other versions of this, but the simplest version that you can think of is if we just take a simple example where, say for example, this is water and this is air. Okay, so they have 2 different refractive indexes. Okay, light traveling from A to B in this context will travel by the path of least time. Okay, so if I pick any other path, okay, as given by the red dots here, okay, and I measured how long it would take to go from A to B, okay, the physical path is the path which is the path of least time. And you can figure this out using a variational principle, okay, and indeed you will use that to derive Snell's law, okay. Now, associated with this is the Huygens principle. This is very similar, or indeed identical to both of these, okay, which says that a wave front is generated by the sum of the circular circular waves which are generated along each point on the wave. Okay, so you can see this construction that I've sort of done rather haphazardly, but hopefully you can understand what's going on here.
What do the dots represent?
The dots are just the points at which you're generating the circular wave from.
Oh, okay.
Okay, so for example, this is where the wave is starting. This is where it is after a little bit, and this is where it is after 2 intervals.
Right. Should the 2 interval point, should that be a bit wider at that point?
Potentially that whole diagram should be.
No worries. Okay.
Alright, so we've done that. So, quantum version of this statement of path of least time, okay, also generated by Professor Carlini in 2005, okay, says that the quantum state travels by the path of least time on the complex projective space, okay, and we're going to get into what a complex projective space means, okay, and the simplest example which I can give to you, okay, is who here is familiar with what the Bloch sphere is? Okay, a two-state quantum system can be mapped to the surface of a sphere. You should be familiar with this too, because it relates to your work on SU2. Okay, so in this case, we have a geodesic that joins any 2 points on the surface of the sphere. Okay, and indeed you can do a calculation which can show that there's a series of curves, okay, which you can show is equal to, okay, so you have a path of least time which joins any 2 points, and then you'll have a series of nodes. Okay, so in this case, the first node will be given by √3 pi/2. Okay, so that's that. That's the basic physical background of what's going on here and why you will be interested in this problem. Okay, so let's get into the mechanics of what is going on here. Okay, and basically just get to start to unpack this statement, because basically we need to know what is meant by a complex projective space, what is a Hamiltonian, what is an operator, okay, what is a quantum state. So what we're going to be working with in this sense, or in this problem, is we're going to be working with a state vector, okay, which you can just imagine as it's a column vector full of complex numbers, okay, or in this case, they're going to be functions of time. Okay. Now, we're going to have a Hermitian conjugate, so because they're complex numbers, instead of just a transpose, we're going to have to take a complex conjugate and a transpose in order to get the adjoint or the Hermitian conjugate. And using this, we can make such things as inner products, okay? Just by putting this together, okay? We can show that indeed, I mean, this formula follows, but we're also going to have it so that all the sum, so these things here are representative of probabilities, okay? Now, what is the sum of all the probabilities? 1, yes?
1.
That's correct, okay? Okay, so each of these is the probability that the state is in one particular configuration or not. Okay, so the sum of all alternatives is equal to 1. You have a question?
Yeah, so just a caveat that, like, it's not necessarily true that size coefficients sum to 1. It's that the squares
The square.
sum to 1.
Yeah.
Yeah, so just clarifying your language, but that's why I was sort of hesitant.
Yeah, that's all right. Okay, now we can do other things as well. So we can make an outer product, okay, which it's just going to be some matrix. I'm not going to write out the whole thing because it's complicated. So 1, 2, 2, so I have to do that all the way down to Cn squared. And we call this thing the expectation value. Okay? And the final thing that we need to play this game is the trace. Now, is everybody here familiar with what the matrix trace is? It's the sum of the diagonals. Okay. Basically, in the problems that we're going to be working with, trace is very important because trace is the concept of measure, or the concept of like an inner product of a matrix. Okay, so it will give us basically a distance, or you can think of it like a distance. So that's the basics of what's going on here. Let's see if we can do something with it. Okay, so brachistochrone. Start with some maths. Okay. So formula for energy variance is very simple. Okay. I'm sure we all know this from basic statistics. Okay. The variance in anything, well, that's the expectation in h squared minus expectation. Okay, so the statistics formula, would you be familiar with something like p of x squared minus, would you guys be familiar with the formula like this?
Yes.
Yeah? Okay, so
What's H tilde?
H Hamilton's.
Alright.
Okay, so we'll get into this.
Yeah.
Alright, so that's what that is. Okay, and now we're going to set something up. We're going to call it this strange and very useful beast is called the Fubini Studi metric. I'm going to pronounce it right because my old professor used to get a bit picky about it. It's like it's not the study metric, it's the Studi metric. Okay, so the Fubini Studi metric, okay, ds squared, okay, is equal to 1 minus sine plus d sine. Okay, and this is all just pretty much given, but you can do some calculations, and what you will find is that this thing can be written like this, okay, where P is the outer product of the state with itself. Okay. So, yep.
You mean metric in terms, in the sense of a measure space? Okay. And
Oh no, what is all?
I'm still.
Okay.
So you need, what metric space are we in for this?
Complex projective space.
Right. Okay. Yeah. Which metric?
So this is.
So you're asking tricky questions?
Yeah. Yeah. They're getting me stuck on the definitions. Alright. Okay. So that's what this is. Okay. And I'll show you how you can use this thing to get something done. Okay, so who here is familiar with the concept of action principle or orange equations? Yeah, yep. Familiar with it? Yeah, a little bit. Okay, so in this case, we're dealing with something. Okay, firstly, what we do is we define the velocity of the state. Okay, so in this case, associated with this metric, we say that the velocity is equal to ds dt is equal to the variance in P. Okay, so, and we have an action principle which is given by, I'll just show you what all these bits are. T plus T. Let's see. And I'll just show you what all the little bits are. Okay, so LT in this case, well, we want to minimize the time, right? So to minimize the time, and it's kind of a trick, but you'll understand when you do it. Okay, so if I just write 1 over delta E ds to t, well that's equal to 1. Okay, so when I write it up here, that will be something that is like integral detail. Okay, so that will be minimizing the time taking. Okay, and using this expression over here, okay, well we have ds. Okay, so we just put everything together. Okay, and we get 1 minus expression side dot 1 minus p side dot delta e. Okay, so that will be the first term. Now the second term.
Yeah, dots the indicate derivative.
Yes,
Okay.
that's correct.
Okay.
Okay, because you're dividing by dt.
Yeah, that's just the open circle. Just
Oh, sorry.
That's right.
Here you go. Yeah, feel free to ask any questions if it's a bit confusing or whatever. Okay, now the second part of this. Okay, so I've got, oops. Phi dot psi minus psi dot phi. I'll explain what all these bits are. Okay, so what this bit does is essentially just holds everything to follow the correct quantum dynamics, which in this case is the Schrödinger equation. Okay, and the third bit, you will know this if you've done any work with Lagrangians and stuff, is you need some sort of Lagrange multipliers which give the constraints on the system which we're working with. And for now, we're just going to write this in the form some constraints on the Hamiltonian operator h, okay, times some constants. Okay, so this one minimizes the time taken between any two states. This one forces it to follow the Schrödinger equation. This one is a set of constraints on this Hamiltonian operator h, okay? And basically, now we have a system of equations in the variables psi by the Hamiltonian h and the variables lambda j. So these are the variables which we now need to do variational principle on, okay, to find the Euler Lagrange equations and basically use that to evaluate the system. Okay, so we can solve this thing called the quantum brachistochrone. But now, so FJ is yeah, because H is now H tilde is a variable. Yeah.
You've got lambda j and fj there.
Fj of H.
Sorry. Yes.
Sorry if it's not clear enough.
No, it's quite clear.
Yeah, these things vary.
But you just put lambda j's out there and not fj's in your attributes. So the fj's are kind of fixed beforehand, I think.
Oh yeah, they are fixed beforehand, but we haven't. We'll get into that in the next bit. Okay. So this is a little bit different to standard quantum mechanics in that normally in standard quantum mechanics you would be prescribed what the Hamiltonian is and you will work everything out. In this case, what we're doing is we're setting up the problem and we're trying to find out what the Hamiltonian is. Okay, so I'm going to figure out. Now let's just look at these things called Euler Lagrange equations. I'll just show you one. And then I'll show you a trick so that we can get around it. Okay. So let's just pick a really easy one. Okay, so let's consider the variable psi. Okay, y, y dot. Okay. So the Euler-Lagrange equation in this case will be d dt of dLs over d dot. Sorry. Oh, yeah. Okay, so if we just look at this variable, okay, this variable only appears in the second part here, so we can just forget about everything else. Okay, and if we calculate this, then it's pretty easy. You just differentiate it off, right? Okay, so this bit will be I d psi over dt is equal to, now this part, it's just going to be this bit over here. Okay. So we have this equation. Wow, it's the Schrodinger equation. It's not amazing. Okay, so that's one part. Now you can't really move forward until you specify what the constraints are or what the Lagrange multipliers are. Okay, so we need to talk about that now. So, constraints. Simplest constraints that you can come up with, okay, in this case is f1 of h is equal to trace h squared over 2 minus k. F2 of h is equal to trace of hf. Okay. What does this mean? So this condition here is called isotropic condition. And this is just a linear constraint. And I'll show you what this means. But basically, when you do this Euler-Lagrange equation, but in this case you substitute h, okay, this thing will contribute an amount lambda 1h, and this second bit will contribute lambda 2f. Okay, so we call f the constraint, or it's like saying what is a Lagrange multiplier? Like it's the thing that you use to calculate it. Okay, but anyway, I'm just showing you this for consistency. Basically, once you get this set of equations, you have to do a whole lot of algebra to get the answer. I'm going to show you a shortcut that basically gets you the same answer. But it's not, it's just a shortcut. It's not necessarily the whole proof. The whole proof is a little bit too complicated for this class. A bit too boring. Do you need a coffee?
No. I will by the time. I will before you finish that proof.
Oh, yeah, sure. Okay, so. Now, there was this one mathematician. He was a great mathematician. He figured out a lot of things. He was a very smart guy. Okay, so he came up with this equation. A over dt is equal to h a. Okay. Now, this bracket here, all that means is the difference between h times a minus a times h. Now, because we're working with matrices, it's very important that the order of everything is all kept. Okay, it can be a bit tedious, but it's okay, we'll work with it. Okay, so basically we take the ansatz. Now this equation is true for any operator where A dagger is equal to A. Okay, so let's assume that, well, we could write H. Okay, that's going to give us nothing on the right hand side here.
What's A?
I'm going to show you.
I just generally use
It's
sign.
just,
Okay.
it's just anything.
Oh, right,
It could be anything as long as it follows this.
okay.
Okay, so let's say that and we always have that H is equal to H dagger. That's the definition. Okay, so what we're going to do is we're just going to add this constraint here. Okay, I'm going to say that, well, if A dagger is equal to A and this is a linear operator, then we can just add something like F dagger is equal to F. And then this A dagger will still be equal to A.
And H is our operator on our complex projective space.
Yes.
I mean it before, yeah.
Yeah. H is the thing which drives the state. Okay? Pushes it from one time to the other, basically. Okay? So if I just punch this in, okay, I will end up with the differential equation which is I dt H plus F is equal to HF. Okay. Now, I'm not going to show you. If you want, I can direct you to the paper where you can struggle as hard as I did at one point. But the key point is, if I do the Euler-Lagrange equation in the variable H and then do a lot of algebra, I will end up at this equation that you made. Okay? But the thing is, just by doing this, I can get it in 3 lines. Okay? Now, alright, so basically we have a set of equations which I'm going to write up here so that we can just keep in the back of our minds. So we have trace of h squared on 2 is equal to some constant. We have trace of hf is equal to 0. We have I d by dt h plus f is equal to hf minus fh. Okay, and we also have the Schrödinger equation, I d by dt sine is equal to h of t sine. Okay, so this is basically this is a system of equations, okay, which are all coupled together, and we want to find a way out of that. Can you guys all hear me? Yeah. So I'm just going to do 2 little problems, and I'm going to show you how I use this thing, how you can get an answer out of it. The only other thing which we really need is the concept of unitary evolution. That's pretty easy, I'm sure that you'll mostly be familiar with that. So, unitary evolution I'll just show you what it is. Okay. Basically, it says if I have an operator h of s at some time, okay, then if I apply this, what it will do is it will take me to h of t. Okay, so now this thing which I wrote u of t s, okay, you can do a bit of work and you can show that this thing is equal to minus I from s to t h tau tau. Okay, so basically we're reduced to, we want to find the h And once we've got the H, we find the U, and the U will tell us everything we need to know about the system. Okay, so let's set up the problem. Who here has used the Pauli matrices? Yeah, 1, 2, 3, 4, alright. Okay, so in this situation, we have some matrices which we can set up. Sigma Y, sigma minus Y, Y, Z, and sigma Z. Okay, so now what we're going to do is we're going to define what a spinor is. Okay, so a spinor is going to be something where we call it it's difficult to do bold in text, isn't it? We'll just use, we'll use that arrow on the top, right? Okay, so A dot sigma, okay, in this case is going to be like AX sigma X plus AY sigma Y plus AZ sigma Z. If you write it all down, like AZ minus AZ, X minus Y, AY, AX plus IN. Okay? Everybody okay with that? What that means? Alright, well, what a spinor is something that will follow the rule A dots, and you can prove this using the matrix algebra. It's probably the easiest way. Okay, so if I just multiply these two matrices together, I will get a rule that says this is equal to A dot B times the identity matrix, okay, plus I A cross B dotted with this thing. Okay. So it's an interesting rule because it kind of mixes up the dot product and the cross product. Okay. But this is all pretty normal. It all follows. Alright, so now let's set up a problem. Okay, so basically we're solving for h of t. Okay, so in this case, let's just set up a problem h of t and we'll go, alright, well, h of t is equal to some function to be determined times this matrix plus another function to be determined times sigma y matrix. Okay, we'll just call that A dot sigma. Okay. So trace of h squared on 2, so this equation here, okay, well, this will be equal to 1/2 trace of A dot sigma, A dot sigma. Okay. So that's equal to 1/2 trace of A dot A plus A cross A dot sigma. What's the cross product of the vector with itself?
0.
Right. Okay, so this bit goes. Okay, and we're left with A dot A. Okay, because the trace of an identity matrix is 2 in this space. Okay, so that cancels out that.
And you cunningly put a well half in front.
Hey?
And you cunningly put a well half in front.
Yeah, yeah, very clever that way. Okay. Alright, so oops, let's just grab that. dot A is just A squared. Okay. So if this thing is equal to K, for it to be a proper Lagrange multiplier, that's got to be less than infinity. Okay, so what this says is this vector A here is some finite length. Okay, that makes sense so far.
Where did sigma z go in your H? Did
I'm going to show you. I'm going to show you.
Oh, okay.
Sigma z in this case is going to be the F.
Oh, okay.
Okay, because I'll show you why this is the case.
Oh.
But you're correct. You could set it up using, like, say for example, it could be like lambda z, sigma z here.
And then y was the one.
Yeah. Or, like you could have it so that everything's over here. Okay. So let's solve the second one. Okay, so we've got the trace of HF. So let's just say that F is equal to B dot sigma. Okay. Some arbitrary linear combination. Okay. Well, this thing in this case will be trace of A dot B I plus I A cross B dot sigma. Okay, and we want this thing to be equal to 0. Okay, following this equation. Okay, well, so what that will imply is that A dot B is equal to 0. Which implies that B is equal to 0, 0, I'll just call it omega z. Okay. Can you see why that is true? Yes or no? No.
Well, A is only got coefficients in X and Y, isn't it? And,
Yeah,
and,
that's right.
and B only has coefficients in
Okay, so what that will imply is that F is some other matrix, which is like this. You don't really need the this there. Okay, so we've got most of the problem now, or at least we settled that. Okay, so we've got F is equal to some matrix like that, and H is equal to some matrix which is AX minus INI, AX, so much shorter than this. Okay, and these will satisfy these first two equations, so we've got that. Okay, and we're just going to write this in terms of complex numbers. Okay, so this will just be epsilon, G. Is everybody following so far? And if not, it seems like... Okay.
This side is looking very convenient.
Hey?
Yeah, we're looking very convenient to the field.
Yeah. SU2, right? Alright, so let's set up this thing. Good. So we've got this equation here to be solved. Okay. Which we call the quantum brachistochrone equation. I d t h plus f is equal to hf minus fh. Okay. And I'm not going to do the matrix multiplication for you because that's what computers are for.
You want to become numbers.
Yeah, basically. Look, at one point I aspired to be able to multiply matrices in my head, but then I gave up. Okay. Alright, so you'll end up with this set of a couple of differential equations, okay, which is number 3. Now, we can solve this quite easily. I'm just going to basically just write down what the solution is. Okay, so if we look at the left-hand side here, this omega bit, okay, well, that bit's unchanging, okay, so this thing must be equal to constant. Okay, and the remaining 2 equations in these variables, epsilon and conjugate epsilon, sorry,
What does it mean?
okay. Like, I'm killing your head.
Alright.
Alright. Don't worry, the light is at the end of the tunnel. Okay, so that 2 equations. Okay, both of these are pretty easy to solve. Okay, and indeed, you can write down what the Hamiltonian is. You can solve this, and anybody do it in their head. Thank you. Okay. Sorry, I'll just write it down. 0, epsilon conjugate, epsilon 0. Okay, and what we will get is that this is, it's got complex exponential 0. Okay. And basically I'm going to pull a Swifty. I'm just going to substitute epsilon naught is equal to 5 equal to 5. So we just simplify this whole thing. Okay, it's minus 2 plus 5 e to the 2 plus 5. So that's half the game.
Would it not be minus 5 in the bottom left one?
It is minus 5. It's minus 1 here.
Yeah, but when you distribute it, then you add you get a minus alpha.
That's conjugate.
Oh, yeah, right, okay.
Right. So basically the idea is like if you have some big space, so, or even just with a little space like this. Okay, so in this case we have 3 generators in this space. Sigma y, sigma z, sigma x. Okay. Basically what we're saying is if you draw a bubble around that, then you call that the H, and the F is a linear combination of everything else. Yeah. So when you do, because they're linearly independent generators, when you do trace of HF, you'll end up with 0. So almost on this problem. Okay, so basically what we need to do is we need to evaluate this thing. Alright. Now, dealing with exponential of this thing is going to be comparable, so we need some way to move around it. Okay, and there's an easy way to move around it, as we were talking about earlier. what we do is we diagonalize the Hamiltonian at any point in time. Okay, so I'm sure everybody will be familiar with this from first year linear algebra, or at least that I did. Okay, so in this is the diagonal matrix. And these things is the matrix of eigenvectors. Is everybody familiar with the concept of eigenvectors? This next bit is a trick which I made up. It wasn't written anywhere. So if we consider h of naught is equal to, well, in that case we just w naught L w inverse of naught. So the formula thing. I'll just use this formula here. And what we can do is we can write h of t is equal to w t w inverse of naught h of naught w naught. Then everybody see why this is true. Basically, you're just putting this over here. Okay, so you're writing this thing here in the middle is equal to L. Okay, so this thing is you're just sandwiching on the outside the WTs. And this thing is equal to L, which is we would just move this in here. So, okay, well, that must be equal to this equation. So we must have that this is equal to u of naught h of naught u data of t naught. Okay, so it seems like we should have the equation u of t naught is equal to w of t w inverse of naught. Well, that's a lot easier than evaluating that one. You can potentially figure this one out. Makes sense? Okay, so yeah, there's a few other tricks that go along with it. I'm just going to cut to the end of it really and just say, firstly, how are we going for time? 11.
Where's the sound past?
I'm not really getting yeah, it's a question. No, that's okay. It's okay. Alright. Alright, so okay. Now it's pretty easy. Like you can figure out what the eigenvectors are of this thing. Minus I 2 omega t plus 5. 2 omega t plus 5. You can do some calculations and you'll find that the L in this case is equal to 1 minus 1 like this. Okay. And that will give you enough information so that you can figure it all out. Do this, and you'll find that this matrix you have T best here is equal to E to the 2 I omega T minus S. Okay, and this thing is the unitary operator, so this system is not solved. We figured it out. And really tricky. You could potentially take out one of these exponential factors and you'll end up with something which is like either 2 pi omega, sorry, e to the I omega t minus s, e to the minus I omega t minus s, all times some sort of phase factor outside. Yeah, we'll just take the one that's exponentials out front. Sorry. That's correct. Okay, and like if it gave some crazy answer, like as soon as it starts spitting out, it's just like this, it's working. It's not talking nonsense. Okay, so that's that. Alright. So let's step up a bit. Okay, so we're kind of familiar with the problem that we were working with there. Okay, let's work with SU3. So SU3 is going to be a bit harder. Okay, so imagine we have a matrix like this. Well, it's going to be a bit more difficult. So what I'm going to do is I'm going to show you, basically we're going to solve these three, but I'm not even going to do it. I'm just going to show you what the answer is, and I'm going to show you how to get there. Okay, so if I go through this same procedure that we just went through over here, I'll find the matrix. And this was my master's thesis, so I spent 2 years working on this, slaving, being confused, until I figured it out. Once I figured it out, it was obvious. Alright, so if we go through this same game, and there will be a numerical factor here, but we don't really care about that because we can just absorb it into the time. Okay? So, I'll just write up what the F is for you. 3, kappa star. So if we go through playing this game using H and F, okay, well, these two will satisfy the first 2 equations, okay? In fact, you'll find that something like epsilon 1 squared plus epsilon 2 squared is equal to some constant of the first equation, okay? And the second equation, well, you do the matrix algebra, or just do matrix multiplication like that. Okay. Right, so we'll end up with something like this. Now, alright, we're going to play the same game. So in this case, HQ of T is equal to Q of T L Q of T delta. Okay. Now, working in these high-dimensional matrices is much more complicated because things just don't behave as nicely, but you can still figure things out. Okay, so in this case, the matrix of eigenvectors will be given by indeed we can play the same game, right? And what you will find is that basically, okay, so before you could have potentially exponentiated that matrix with some degree of difficulty, but exponentiating this matrix, yeah. Alright, so what you do is you play the same game. So what we do is we're going to U of T S is equal to U of T Q dagger of S, and voila, we will find the matrix plus T minus S 0 by equals theta sine of T minus S 0 1 0. T minus S 0 plus T minus S, okay, which is an element of SU3. So basically this decomposition is very, very useful because we can work with this sort of complicated time Hamiltonians and still figure out what the exponential is with a minimum of difficulty. Okay, we have time translation domains. U of T minus S is equal to so that's one way of getting at issue 3. Now I assume we've got about 10 minutes left. Is that correct? Yeah. So I'm just going to give you a little tour of another way of looking at things. So we're just going to start from another direction. Okay, so with these sort of problems, there's often the way you can look at things in terms of matrices, or you can look at things in terms of functions. Okay, so we're just going to look at things in terms of functions just for a second. Just assume that we got the same sort of equation as we had before. Okay, so IV phi dt is equal to h phi. Alright, well, okay, and in this case, let's say that the h, have you guys all done like Laplacians and that sort of stuff? You know what a Laplacian is? Yeah, tell us what.
Yeah, second part.
Yeah. Okay, so in this case, use this symbol. Okay. Plus 1/2 omega r squared. Okay. So now this function y, well, that's equal to sine of x. This is a vector x. Okay. That's some function of t. Okay, so you're familiar with how to use a separable solution in a lot of partial differential equations. Okay, so basically this thing here is the potential. Who knows what the potential of the spring is? Okay, so potential for a spring, if you got something which is like d2x over dt squared is equal to minus kx, and the potential energy of that spring is equal to 1/2 kx squared. Okay, that is the amount of energy that is stored in the spring. Okay, so do some magic with this. Okay, and we end up with a differential equation d psi, where this psi is this function here is equal to minus 1/2 del squared side plus r squared side. So we're going to miss it. That's right. Alright, so physicists love these things. They're called raising and lowering operators. Okay, so we've got these things. It's J plus PJ. I'll tell you what these PJs are. Okay, so this thing here, del squared. Okay, well, that's equal to E dot P. Just show you. Okay, so the PJs in this system is equal to minus I d by dxj. Okay, well, we do a little bit of a trick. If we write H is equal to this thing, it's minus 1/2 del squared plus half root of r squared. Do some tricks. Okay. What we will find is that this thing is equal to HJ plus 1/2. Is this familiar to anyone? This bit? Yeah, it's a simple harmonic oscillator, right? Okay. And then what you can do is you go a little bit further. We write Gij is equal to 1/2 AIJ. This thing shift. Okay, and what we can do some more tricks. We can show that this thing is equal to gxx plus gyy plus gzz, just like a trace, right? There we go. So what you can then do is you can show that the generators of algebra can be written as gxy plus gyz. Okay, which you can imagine. I haven't shown this explicitly yet on the way to doing it, but basically it maps to a representation that is like this. Okay, so the thing is that this is a differential operator. This is a matrix. Okay, and you can write out all of the other sort of operators that are associated with it. I'm just going to write out what the important ones are really. Okay, so lambda 3 is equal to gxx minus gyy. So this thing is equal to a matrix like this, and this thing is equal to a matrix like this. So this, I believe, is called the maximum commuting element of the algebra, and this
this one plus this one plus, you can guess what the other one is going to be without looking at the thing too late. Right, so, have this matrix G. Okay, so we'll have this element here. Yeah, well, it's like the sub-algebra, but SU3.
Sitting inside us.
That is correct. Yeah.
So can you step back to the shift operator where you had
Yeah.
H bar, G X, X, G, Y? How did you get to that point there? I just don't understand
Here.
how you. I get you.
I'll show you afterwards. It's actually
Is it-
good proof. Like it.
It's a okay. So this is like a known relation between that.
Oh no! You can. How did I get this?
No, the last one.
This.
Like I get the statement of G.
You can prove it. You just
From this.
substitute it. Okay, and basically you're gonna have like.
Yeah, I assume you skip the details because
Do you know what the? Yeah, I'm kind of
Yeah.
But basically there's a. Do you know what a commutation relationship is?
you do with matrices and stuff like that.
No. It's like you can show this relationship and data is equal to this, or you can show I'll show
Is
you.
it the lead bracket? There?
Yeah.
Okay.
Yeah. I'll show you it after the class. Alright, anyway. This is the bit that I like. Okay. How much time have I got? 5 minutes. Alright. So, turns out that I can write this shift operator in this really nice form. X I X J plus I2. Who here knows what a Levi-Civita symbol is? Yeah.
Delta IJ.
This thing.
Are you using epsilon
No. Delta IJ is just that's the Kronecker one.
there? Oh, that's Kronecker
Yeah,
delta.
this is the Levi-Civita one.
Oh, okay.
So it's 1 if IJK is cyclic,
Oh,
minus 1 if it's anti-cyclic.
yeah.
So basically, what this is the this is a Cartesian tensor. What the first part of it is, and then we have this anti-symmetric bit. Okay, and I'm probably going to cut off here. Okay, but you can do some more tricks that basically just show that like any tensor can be given in terms of its symmetric and anti-symmetric components. Okay, this is known. But what you can do is you can take what is called a spherical representation of a tensor. Okay, so any tensor can be given as a trace plus this anti-symmetric part plus the symmetric part minus the trace. Okay, and the second part will be what is called a spherically symmetric tensor. Okay, and I'll just show you basically what it is. So let me cut off. Alright, so in this case, you can write it as delta J GKK plus GIJ minus GJI plus 1. Alright, so this is this like you can see that this part here, okay, in fact, it's here, so you can make that, this is what the delta of JH, okay, so GKKs is equal to that. And this anti-symmetric bit, well, that's going to be like an angular momentum. Yeah? And you have this final bit here, which they call it nuclear quadrupole tensor. Okay. Thanks, guys.
Thank you.